All right, class, now that we've got some of the basics down for scientific notation, let's try to apply what we've learned, and we're also going to lean heavily on our exponents, our rules of exponents. As I have already said many times in pre-algebra, the great thing I love about 8th grade math is that you've entered a world where things don't leave. Right? Everything just keeps building, it seems. So we're going to do some math operations with scientific notation. We're going to start with adding and subtracting. All right, so in this example, this first example, notice I have 2 times 10 to the 4th plus 3 times 10 to the 4th. Now, one of the big, really important things is right here. We've got a common base, but also raised to a common exponent here, and that's going to be very important. So once we have that, both 10 to the 4th, I'm kind of dealing with the same numbers. In other words, you can almost think of it as the exponent, the decimals are lining up. So in this case, you're going to add 2 to 3 and get 5, and that's going to be 5 times 10 to the 4th. Notice I didn't do anything with the base or the power. It's 5 times 10 to the 4th. I think this is similar to adding 1/3 plus 1/3 and you get 2/3, right? You don't change the denominator. In this case, treat it the same way. You're not going to change that base or its exponent. Let's illustrate this. 2 times 10 to the 4th, well, that's 20,000, isn't it? So here's my decimal. I move it 4 places to the right. 3 times 10 to the 4th, well, that's 30,000. Well, let's add those, and we'll get 50,000. Now, that's some nice mental math. But wait, what's 5 times 10 to the 4th? Well, there's my 5, there's my decimal. I've got to add 4 zeros. Look at that, exact same thing. Isn't it a whole lot easier to learn the rules rather than having to add large numbers? And let's face it, these are easy numbers to work with. 20,000, 30,000, 50,000. But what if this number were 2.37809 times 10 to the 7th? And well, you get the point. All of a sudden, it can become a lot more complicated. These simple numbers enable us to learn the rules. So again, common base, common exponent, I'm just adding them up. But look at what happens in our next example. We have 2 times 10 to the 3rd plus 5 times 10 to the 4th. So in this case, we've got to rewrite something. Let's do something here. What if we said this is 0.2 times 10 to the 4th plus 5 times 10 to the 4th? You see what I just did? I made both of them, they had the same base, but I needed the exponents the same as well. I needed to go from a 3 to a 4. So to do that, I had to move the decimal 1 place farther from its original location. I hope I can illustrate that better in a moment. But I needed these two the same. So in that particular case, now that I have the same base exponent here, okay, I could say that this is 5.2 times 10 to the 4th. And I'm going to say that's my final answer. All right, well, let's come back up. 2 times 10 to the 3rd is 2,000, right? And that's going to be plus 50,000. 5 times 10 to the 4th. Well, that's 52,000. What's 52,000 in scientific notation? The decimals here, 1, 2, 3, 4. That's 5.2 times 10 to the positive 4th because I need to go back to the right to get back to my decimal in standard notation. So look at that. The exact same thing. Whoop. Circle the 4, and that's part of the answer as well. The exact same thing. So here's the rule. You need to have these need to be the same. If you're going to be adding or subtracting, those have to both be 10 to the 4th, 10 to the 2nd, 10 to the 3rd, whatever the case is. And I would take the smaller one and adjust it to equal the larger one. All right. Let's look at multiplication. This one's pretty straightforward. If we're going to multiply, we're going to say, what if we rewrote it? We could say 1 times 2 times 10 to the 3rd times 10 to the 4th. If we wanted to gather our bases, 1 times 2 is just going to be 2. It's got our straight integers there. Times 10. Now, what do we do with exponents of common bases? Well, when we multiply, we add them. So that's going to be 2 times 10 to the 2nd. We would actually take all of that and just write it this way. 2 times 10 to the 7th power. 2 times 10 to the 7th power. Well, let's illustrate this. This answer, 1 times 10 to the 3rd that's 1,000. And we're going to multiply that times 20,000. All right? 2 times 10 to the 4th is 20,000. What does that equal? Well, that's 20 million, isn't it? Let's come up here. What if we had 2 and we need to add 7 zeros to the right? That's 7 zeros, isn't it? Same thing. Okay? So when we're multiplying, we're going to multiply our integers together, and then we're going to multiply our bases and their exponents together. And when we multiply common bases, which in this case 10 is the base, we're going to add the exponents. Well, what about when we're dividing with scientific notation? In this case, we've got 2 times 10 to the 5th divided by 1 times 10 to the 3rd. So 2 divided by 1 is, well, it's 2 times 10, 5 minus 3. So that becomes 2 times 10 squared. Okay, that's our answer there, 2 times 10 to squared. Let's come up here and let's roll to the right. What's 2 times 10 to the 5th? Well, I'm going to add my 5 zeros. That's 200,000, and that's going to be over 1,000. What's 200,000 divided by 1,000? It's 200. What's 2 times 10 to the 2nd? Well, that's 200 as well. Exact same thing. I'm hoping by showing you the actual arithmetic and seeing that we get these same answers, you can understand why these rules actually do work. It's not something that we created out of thin air. They actually do work. Let's look at one more example. 2 times 10 to the 3rd divided by 1 times 10 to the 5th. So 2 divided by 1 is 2 times 10, 3 minus 5. Negative exponent, 2 times 10 to the negative 2. Now we can actually leave that. You're like, wait, it's a negative exponent. But with scientific notation, it's okay to leave that because that's telling us which direction the decimal goes. Okay, so that's telling us something very, very important. So what if we come over here to the right and we say, well, what's 2 times 10 to the 3rd? That's 2,000. What's 1 times 10 to the 5th? That's 100,000. Now, all of a sudden, this should start making sense. This is not going to be a whole number, is it? This is going to be a number between 0 and 1. Well, what's 2,000 divided by 100,000? It's 0.02. Hey, what's 2 times 10 to the negative 2? You're right. It's 0.02. All right, so whether we just do the straight arithmetic or apply our scientific notation rules and our rules of exponents, we're going to get the same answer.